Welcome everybody to this TMS seminar that today will be held by Dr. Tommaso Salzillo. Tommaso Salzillo graduated in industrial chemistry in 2011, and he received his PhD degree in physical chemistry at the University of Bologna. He was a Marie Curie postdoctoral fellow at the Institute of Science of Materials in Barcelona, where his research project was focused on polymorphism and morphology control in flexible organic electronic devices. Currently, he holds a position as a senior postdoctoral fellow at Weizmann Institute of Science, and he works on a project regarding the lattice dynamics of late halide and chalcogenic perovskite in bulk and thin film for solar cell application. His research interests include polymorphism in organic semiconductor and active pharmaceutical ingredients, solid-state photoreactions, and vibrational spectroscopy. Today, he will talk about us about probing crystal dynamics by low-frequency Raman spectroscopy. Please, Tommaso, when you want, you can start.
Okay. So first of all, thanks Luisa for the nice introduction, and I would like to thank also Sarah for inviting me for this opportunity. And as you said, I will talk about the use of low-frequency Raman spectroscopy for the study of molecular material, and in particular for the study of polymorphism in molecular material. So, in general, I will introduce today, before to start with some example, I will introduce what is the polymorphism and which are the consequences of polymorphism on the structures and the property of molecular material. Then I'll say something about the correlation between X-ray, low-frequency Raman, and how we can use both techniques to understand completely different things, but they are very complementary techniques that we should use for studying molecular material in particular. And then I'll give a couple of examples. The first one will be the polymorph screening in organic filter effect transistor in situ. And then, if I have time, I will say something about the use of low-frequency Raman for a more exotic application, the study of solid-state photoreaction in single crystal. So, first of all, I'm quite sure that a lot of people have observed that we have different material with different shape and different composition. The phenomenon of polymorphism is spread over everywhere in all the field of material science. Here I'm reporting a very famous example, the carbon. In this case, it's not polymorphism, but it's the phenomena of the allotropy, because we are talking just about one element, the carbon indeed. And the carbon can crystallize in solid state in two different structures. It can crystallize as a graphite, which is a very soft material, with very low cost. It's a very low cost material. And then it can crystallize in diamond. I think everybody knows about diamond. It's an amazing material, and is the hardest material in the world, apart being also one of the more expensive. But today we will talk more specifically about polymorphism, that is the same ability of another kind of material to crystallize in different structures. And in principle, molecular material are solid made not by elements, but by molecules. So molecules are keeping together by weak interaction. This interaction can be van der Waals, pi-pi stacking, or hydrogen bonding. Here I'm reporting an example considering a rigid organic molecule. If we consider the rigid organic molecule as a brick, we can make a wall organizing the brick in a different way, and this is how the molecule can pack in solid state, giving two different polymorph, polymorph 1 and polymorph 2. Of course, when the molecule is not rigid, the situation is a bit more complicated, and the way that the molecule can pack in the solid state can be, let's say, endless. This is a very nice question. Usually people always asking me how many polymorph a molecule can make. So I'm always reporting a very nice statement by Macron. Macron wrote an amazing book in 1965 just about polymorph. And I like always to report this statement by him, and he's always say that the number of polymorph of a specific molecule is always correlated to time and the money spent in researching other polymorph. So now I will go more bit in practice, giving some daily life example. I know that a lot of you don't know that that chocolate has a lot of polymorph, and that it is also crucial for the food industry. Indeed, chocolate is a very complex material made of different elements, but the main component is this molecule here, the fatty acid. There are three major component of the chocolate of this fatty acid with different alkyl chain and different saturation of this alkyl chain. But in general, as you can see, this is not a rigid molecule, it's a flexible molecule. So we just go back to this more complicated case. So what we are expecting is a lot of polymorph, a lot of structure for chocolate. And indeed, if you look in just by Google, you can find the same picture that I'm presenting here. Chocolate has 6 polymorph, and just one is the one that the industry wants for the commercial use. And this is the polymorph number 5. I'm also sure that you have seen at least one in your life the phase transition of chocolate. Indeed, it's usual to leave chocolate close to a hot surface, or even the common mistakes is leave chocolate in the car during summer. And so what we observe is the formation of this white material on the surface. This is called the blooming of chocolate, and is due to the phase transition from form 5 to form 6. And the white stuff that you can see on surface is the segregation of the elements that are dispersed in the fatty acid matrix. So just a couple of examples more that we can encounter in our daily life. Paracetamol. It's always a very known material. Everybody already, when you have fever, paracetamol is working very, very good, at least for me. Paracetamol has 3 polymorph, and the big issue for the polymorphism in active pharmaceutical ingredient is the solubility. Indeed, as you can see from the graph here on the right, if the solubility is too high, the concentration in our body is too high, and then can be toxic for the human body. Or in the other way around, the solubility can be very, very low, so it's not efficient for the pharmaceutical activity. And then we can get the polymorph with the right solubility rate, and this is the right polymorph that the industry want to sell. Just quickly, another example recently from the literature. This is the molecule that the group here, Cappuccino et al., they synthesized. 4 polymorph for different color, and this is very nice for application in light emitting dyes. So it's very easy to modulate the emission of the device, just changing the experimental condition to grow the film or the single crystal. So before to go a bit into detail for the first example, I say that I will talk about Raman, how to use Raman for the characterization of molecular material. So a couple of words about what is the Raman effect. Raman spectroscopy is using a monochromatic light, usually from a laser. And this monochromatic light interacts with the material, with the molecule, with the atoms. And then there is a couple of effects that we can observe. The light is after the interaction is scattered, and can be scattered in an elastic way or inelastic way. If it's elastic, we get exactly the same energy of the incident light. If it's inelastic, we can get a more energetic scattering or a less energetic scattering, and this is the Stokes and anti-Stokes branches of the Raman spectroscopy. What is possible to observe here from the graph, from the diagram on the right, that the difference between the incident light and the inelastic scattered light is exactly the energy of a vibrational level. So in other words, with Raman, we can detect, Raman is a vibrational spectroscopy, very similar to infrared, but with different selection rules, so we can get different information. Here on the bottom, I'm reporting a very common Raman spectrum. This is what we obtain usually when we measure the Raman of some material, and this is specific for a molecular material, solid state. So the graph can be divided in two main parts. The high frequency, this that I highlight with a green color, and this is the range where we can observe all the vibration of the single molecule. So we can observe all the functional group like C double O, C double C, all the stretching, bending, and so on. And the other range is the low frequency, the one that I just highlight in blue with the blue color. And this is the range below 150 wave number. It's not common because it's not too easy to reach this range with a commercial Raman instrument. But this is really useful for the study of molecular crystalline material. Indeed, here we don't observe anymore the vibration of the single molecule, but we can observe the vibration of the crystal lattice. So, in other words, is the fingerprint of each specific polymorph. So here, just a comparison, very quick comparison between X-ray and Raman. I mean, when the people talk about crystal structure, polymorphism, the first thing that you keep in mind is I want to use X-ray to characterize. And actually, terahertz is complementary to X-ray, and I like to make always this comparison. While the X-ray is taking an instantaneous pictures of the system, the Raman is terahertz region. Raman is able to collect, to record the dynamic of the system. And here I'm reporting a very easy example. Coronin is this molecule. I took as example a very rigid molecule, so we don't have other problem of different configuration in solid state. And if you measure the single crystal of coronin obtained with different condition, you can have these two crystal structure, alpha and beta, gamma and beta. These are two polymorphs that are enantiotropic, but anyway, this is another detail that is not important. And now let's see what we can get by low frequency Raman. We can observe here the low frequency below 150 wave number that beta and gamma have completely different pattern. So even a very small change in the crystal lattice generate a completely different dynamic of the system. And here, just to make the things quite clear, by DFT we can even calculate which kind of motion we are looking and which kind of symmetry are each peak. And here I'm reporting just two peaks that have exactly the same symmetry for the same polymorph, for the two polymorph. And well, what is clear that the movement and the amplitude of the movement is different. Okay, now that we have more or less clear what is the terahertz Raman and how we can use it, I will explain one example, one of my last work. So my interest, as Luisa said, is the study of polymorphism in molecular material, and especially for application in field effect transistors in flexible device. So this is a molecule that we synthesized. Actually, is an organic semiconductor that the main characteristic are the aromatic core with a strong pi electron conjugation. And then this aromatic core can be functionalized chemically with different groups. In this case, we use oxygen to modulate the HOMO-LUMO band gap. And then we use a two very long alkyl chain to make this molecule very soluble. Soluble because usually molecules are more appealing if they're soluble because can be processed by solution method that are cheaper compared with the evaporation. So this molecule can be crystallized in two different structures, one called bulk, that is characterized by pi-pi stacking of the aromatic core, and the other one is called SIP, that it stands for surface-induced polymorph. Surface-induced because it has been observed that is a metastable phase. Indeed, it's very easy to get this structure by drop casting of a solution. But what happened with time and by solvent vapor annealing? By time, more or less 3 months, and by solvent vapor annealing, the structure, the surface-induced, move to the bulk structure, and there is a complete phase transition. So if you are enough gentle to remove this crystal from the surface, you can perform single crystal X-ray diffraction, and you get that you got a complete phase transition from surface-induced to the bulk. So our idea was to process this molecule and making a field effect transistor. Here I'm reporting just a general scheme for organic field effect transistor. I like to call a sandwich device because it's made of different layers. So there is a substrate, a dielectric, and then there is a active semiconductor layer with source and drain contact that are the contact used for the electrical measurements. So as I was saying, we made this molecule soluble, inserting the alkyl chain, and indeed we were using a cheap and very spread now technique to make film. This is called bar-assisted meniscus sharing. In other words, it's a hot plate where we place our substrate, and then there is a bar, this that we can see here, a metal bar that is spreading the solution on top of the substrate, and the hot plate, by heating the substrate, help the evaporation of the solvent. So the results is a very thin layer. We are talking about from 25 to 200 nanometer by changing the speed of the sharing and even the temperature of the hot plate. And what we were doing here, using two different approaches. The first approach is making the film just using a pure solution of the semiconductor, and the second approach using the solution of semiconductor in blending with an insulator polymer, polystyrene in this case. So okay, we made the device, and then we were measuring the electrical performances. For field effect transistor, maybe Rafael last week explained everything, so I'm not going to say a lot of things, but just to remember, the charge carrier mobility is the main parameter that the people in this field are using. And here was the main parameter that I was plotting in this graph versus time to understand how stable are the devices. What is nice is that we can observe the device made with a polymer agent, are more or less stable with time, till a year and a half, more or less. While a device made with a pure semiconductor, they have a, let's say, quite good mobility at the beginning, and then I can observe a huge decrease till reach 300 days, and I don't observe any more electrical performance. So it's like the device is dead. So our idea, sorry, it's not moving. Okay. So our idea was to understand what was going on in this device. And here I need to introduce something that I didn't say before. Both the polymorph, the molecule inside the crystal structure, are organized in the same way. In the same way, it means in the stand-up configuration. So all the molecules are perpendicular to the surface versus the main axis of the molecule. So who is expert in X-ray can understand already that it's quite complicated to discriminate which polymorph we have in thin film. The X-ray can have different configuration for the measurements, but for film the best configuration is the specular X-ray. With this configuration we can get just the out-of-plane diffraction peak, and here I'm reporting the simulated peaks RD of the bulk phase and the simulated of the SIP phase. And as you can see, comparing with the film, the peak that we can see from specular X-ray are just the progression of 0, 0, 1 plane. And they are exactly the same for surface induced and for bulk. So let's say in this case, X-ray doesn't help a lot in understanding what's going on. So our approach was, why don't use Polarized Raman? And indeed, we performed Polarized Raman of the bulk, of the crystal of bulk phase and surface induced. As you can see, the low frequency Raman are really different, and it is possible to make a discrimination between the two polymorphs. It's even more clear if we observe the very low frequency peak, that is 12 wave number for the bulk phase and 7 wave number for the surface induced. You can see clearly that the vibrations are completely different and the dynamic of the system is different even if they crystallize in stand-up configuration. So just going back to the film that we prepared, so we observed that for the field effect transistor made just with a pure semiconductor, we had a decrease and then the device was dying just after 300 days. So we observed also the polarized optical microscopy, and what we observed that for the film made with a polystyrene, the morphology is always the same. while for the film made with a pure semiconductor, there was a quite strange change in morphology. And well, the other advantage of Raman spectroscopy, that is possible to couple the spectrometer with an optical microscope, and in this case we are able to measure with a micrometric scale the Raman spectra. And indeed we were able to measure this different domain just created on top of the film, and we were able to discriminate between two polymorphs. So it seems that the semiconductor without the blending gadget after 3 months changed from the metastable phase to the bulk phase. So just to understand the entire picture of this transformation, we perform also atomic force microscopy with this nice technique called layer by layer peeling experiment, and we were able to understand the polystyrene for the film made with a polymer agent. The polystyrene go on the bottom of the film, passivating the silicon oxide, that is the dielectric, and freezing the surface-induced structure, which is also the best structure for the semiconducting properties. So quickly, now I'll jump on the second example that is a bit more uncommon and unconventional. This is the chemical reaction in solid state that I like to call chemical reaction in cage, because in some way the crystal lattice is influencing the reaction. So the solid state reaction started some years ago, the study of this reaction, and actually surprising, when I came here at Weizmann Institute, I discovered that one of the first studying this reaction was Smith, and was a professor here at Weizmann, and he made the first study, and from the first study he made this topochemical principle. Topochemical principle, it means that from experimental data, this professor realized that not all the chemical structure can allow the photoreaction or the thermal reaction, but you need to match some specific criteria. And these criteria are two. The first criteria is that the molecule should be well oriented in the crystal lattice and available for the reaction. And the second criteria is the reaction site should be not longer than 4.2 angstrom. And here I'm reporting a classical example, the photoreaction of cinnamic acid. Cinnamic acid has 3 polymorphs, alpha, beta, and gamma, while the alpha and beta are available for the reaction. Indeed, the distance between the CC double bond sites is below 4.2 angstrom. The gamma polymorph is too far and is not possible to react. Then with the years there were some other study, and it has been discovered that at the end that there are some exceptions to the topochemical principle, and there are some not topochemical reaction called, and this reaction occur in a different way, and the theory is by Kaup in 2003. All this is for make a bit introduction about the photoreaction in solid state, and now some application. Okay, it's not working. In theory here we should see something, but anyway, one of the application of the photochemical reaction in single crystal is the use of this system as a photomechanical actuator. What does it mean? It means that the crystal during the reaction moves, and so in other words, it's possible to transform light energy directly in mechanical energy, jumping the step of producing energy, electrical energy. And here, this is the crystal. It's very, very thin, but it undergo a reversible transformation. By UV, you get the bending of the crystal, and by visible light, it's possible to recover the shape of the crystal. Here on the right, you don't see the movie. I don't know why it's not working, but anyway, the crystal is able to move the gear on the right. Other applications for the solid-state photoreaction are solvent-free stereoselective reaction, and if there is a synthetic chemistry, you can understand it's very good to have the molecule freeze in solid state so they cannot move. And then the last example that I'm reporting here, the use of this solid-state photoreaction has memory and switches. So this was one of my interests during my PhD thesis, and I'm still studying this system. Here I'm reporting all the system that I was studying by confocal Raman microscopy in low frequency range. And now I would like to show why this technique is very nice to understand and to study this system. Here I'm reporting all the system that I study, but in principle today I will give some information about the reaction here on the bottom. It is a non-topochemical reaction anyway. So the system is these derivatives of the anthracene, 9-cyanoanthracene, that undergo a photodimerization with a wavelength around 300 nanometer, and then it's also reversible. The reversibility can be achieved by deep UV irradiation, or just by heating. As I was saying, this is a not topochemical reaction. So what we were expecting is that the shape of the crystal is destroyed during the reaction, and indeed here you can see from the optical images. But the point of today is try to understand how to use Raman for the study of this system. And here I'm reporting the Raman spectra as an evolution of the time in both the range, intramolecular range, so high frequency here on the left, and low frequency, where we can detect the lattice phonon, so the vibration of the lattice. What is really, really strange is that after 30 minutes, you can see that we can see already the reaction is occurring. So we can see already some peak that belong to the photodimer. So the reaction is occurring very, very fast. On the contrary, by looking the lattice phonon in low frequency range, we can see a real change of the spectra just after 6 hours, and this is something that just makes us very, very curious. So we decided to make a global fit, try to find an equation that can fit our data, and try to study the kinetics of both transformation, molecular and lattice transformation. This is something that is let's say not easy, but it's very nice to do by Raman. By X-ray there is some problem because X-ray can see just periodic structure. In this case we can probe at the same time and the same spot both transformation. But anyway, what we found is that the lattice transformation is very, very slow, and it starts to occur only after the 70% of the molecule are already reacted. So here we have a lot of data missing because, of course, also Raman has its limitation, but our plan is to study other systems and try to understand if this is a common behavior or not, or is a specific behavior just for this system. Anyway, my goal was just to show how it can be used, the Raman, for the study of this very strange photoreaction. And well, just to conclude a bit what I was saying today, let's say we used the Raman spectroscopy for study two specific cases, the characterization of polymorph in thin film device in situ. We are able to use Raman also for the study of the solid state reaction, but of course these were just a couple of examples. There are some other applications very useful that can be done. And here, just to report others, is the screening of polymorphism in active pharmaceutical ingredient. Other application is the use of Raman mapping that can be very useful for the phase mixing or concomitant polymorph, as reported here. It seems that the crystal is a single crystal, but instead, by looking by Raman, there are some different domains inside. And then I would like to report one of my last study, the use of terrorized Raman to study the disorder of the phase transition under pressure in a diamond anvil cell. So the last slide is just for some acknowledgement. I would like, first of all, to thank my PhD supervisor, Professor Aldo Brillanti, who was able to transfer me a bit of his knowledge about the molecular material. Then all the solid state research group in Bologna, Elisabetta Venuti and Raffaele Della Valle, and of course my host group here at Weizmann, Omer Jaffe Group, all the collaborators in Europe, and of course all of you for your kind attention. Thank you.
Thank you, Tommaso, for your seminar. Very clear and very interesting. If there are questions, please write on the chat, and I will read them. So, if there are still no question, I have some curiosity. I don't know. You told that you explained us that Raman and spectroscopy and the infrared spectroscopy with Raman, you can study the same operational level of infrared spectroscopy, more or less. Which are the advantages of one or another technique? When it's better to use Raman spectroscopy or infrared spectroscopy? Are there some advantages that of one technique or the another?
Well, this is a nice question, but actually I don't see any advantage of, I mean, I would say that I prefer Raman because I'm doing Raman, but in principle the two technique infrared and Raman, they are complementary. So complementary, it means that you can get, of course, always vibrational information, but they are different. Not all the vibration that can be observed in infrared can be observed in Raman. Sometimes you have the mutual exclusion and sometimes not. Then from an experimental point of view, infrared has some limitation because infrared you are using a broadband, a broad source. So the classical example is the Raman mapping. Raman mapping, we can go even to 300, 400 nanometer of lateral resolution. With infrared, there is a very limitation for this because the light that you're using is from a broadband, so it's from far infrared to mid infrared and so on. So the lateral resolution for infrared, even if you're using a microscope, is much higher. So, and sometimes people use synchrotron light to increase indeed this lateral resolution. Yeah.
Thank you. I don't know, Professor Teti raised her hand. I don't know if she wants to.
Yeah, she raised the hand.
Yes. Yes, thank you very much. It has been really interesting. I'm a biologist, so I don't know anything about this, but I was impressed by your presentation. I have a couple of questions. One is the polymorphism a feature only of organic matter, or does it occur also on in inorganic molecules?
Okay, no, polymorphism occur also in inorganic molecules, in inorganic material. Indeed, now a material that is studying a lot, and I'm also starting with low frequency Raman, are perovskites. Perovskites are all inorganic, and they have a different phase transition, especially with temperature. And it's important to understand when this phase transition occurs, just because perovskites are amazing material now for solar cell, but it seems that they are quite unstable, and the instability is due to this phase transition. So yeah, the answer is yes. It's also for inorganic material.
Well, I'm curious about that because I work on bone, and you know that the bone is infiltrated with the crystals of hydroxyapatite. So I was wondering if there are other structures of hydroxyapatite that could not fit with the bone function. Probably this is far from your knowledge.
I mean, I never tried this material actually. What I tried was mainly inorganic material like titania, titanium oxide. Titanium oxide has 3 polymorphs, so I'm quite sure that maybe can happen also for this material. Then find the right condition to get different polymorphs. This is another. It depends on time that we spend on it. So.
Yeah, and another point is that I'm impressed about the photomechanical actuator, and I was wondering if there are already applications in everyday life, or if you can predict some specific application for the future.
Right now, the closest application is the use of this photoreaction as a storage device, because actually you can, it's like having an hard disk made of organic material, then you can use a laser and then print the information. There are several works that they want to use this material for several other applications. One other application is to use as nano tweezers inside cell. It's still far, but now people are working a lot on this field. But real application, no, I didn't see any of this at the moment.
It's good for you, because in the future, maybe you can be the first one.
I hope so.
Thank you. And I would like to encourage the audience to not write in the chat, but just open your microphone. I see Marco, for instance, ready, because in this way it's more interactive. Thank you.
Yeah, I agree.
Please, Marco, if you have a question.
Yeah, I have just a curiosity. Since you mentioned that the polymorphism of many organic molecules depend on time, can you use it to date, for example, paleontological specimens or things like this, like what you do with the carbon-13?
It's a nice question, but I would say no, it's not possible. No. But it would be nice. It would be really nice.
Okay, thank you.
Are there other questions? Professor Fred, again,
yes.
Do you want to ask?
Yes, sorry, it's just to make some jokes. My husband is a chocolate addicted, in my opinion. So is there any good news that I can bring to him about the chocolate? Because I was impressed also by these changes in the chocolate.
Yeah.
So what is the best one?
The best one is polymorph 5. And actually, when I started studying polymorphism, I found this thing, and I was like, wow, I have no idea that chocolate can have this huge problem. But then looking literature is it's a serious problem, because people don't want chocolate in another polymorph. The reason is, first of all, the melting point. And then, I mean, when you put the chocolate in your mouth, you would like that the chocolate start melting in a specific way, not just completely instantaneously. So the polymorph 5 is the best one. And the industry are using this process called tempering, just for making sure that the polymorph is the right one. So
can I make a recommendation to the audience? Buy the Italian chocolate, because it's really very good, and save the work of the many people.
Yeah.
The best polymorph 5.
Yeah, polymorph 5.
Polymorph 5, the best one. Other curiosity question. There is someone that wants to talk. Matteo, maybe? You have opened your microphone. Do you want to ask something? No. Okay. I have another curiosity on your presentation on the first part in the field of organic semiconductor. Why did you choose that organic moiety, that with the thiophene, if I'm not wrong? Why did you choose the organic molecule? Then you linked a long alkyl chain to make it soluble. But why did you choose that?
Okay, because there are several molecules that now are used for organic semiconductor. I think that the field, if there is someone about the field organic semiconductor, for sure they remember pentacene and rubrene. They're amazing for their properties, but the big problem is they're unstable. So this molecule, the aromatic core that I was presenting up to now, is one of the best as a stability in atmosphere. The big problem is not completely, but is insoluble. So the first modification that we made was just to put alkyl chain. So it was very, very soluble. But the second problem was now I'm going a bit into detail for organic semiconductor, but without the oxygen, the molecule has a Homo and Lubon level that they don't match with the source and drain contact. And not matching, it means very high contact resistance. And this is why we decided to put also oxygen and to decrease the contact resistance. But mainly the choice for this molecule is the stability. They are really, really stable.
Okay, and another question always linked to this topic. You used silicon oxide as support. You can change, it's possible to change the support. Even in this case, there is a reason why choosing silicon oxide is cheap. I don't know.
Yeah, no, it's a good reason. I mean, indeed, especially for this material, it seems that the phase transition is induced by organic and inorganic interface. So it would be really, really nice to change the dielectric. Indeed, it's something that I'm trying to do. The reason why we use silicon oxide, because we can buy the silicon wafer. The silicon wafer, it means a silicon doped, that is already the gate, and silicon oxide, thermal oxide, with a specific thickness and a specific capacitance. So let's say that silicon oxide wafer are used in organic electronics as a benchmark. So everybody, the first measurement that you do is on silicon oxide. So you can get the parameter, mobility, threshold voltage. And then when you have this parameter, you can compare with other in literature and say, okay, this is a good semiconductor. And then the other step is say, well, let's change the substrate. Let's try to find a flexible substrate. Because, yeah, we always say that organic electronics is amazing because the molecule can be flexible, but we still make device with silicon oxide that is not so flexible. But it's the benchmark for the field at the moment.
Okay. Thank you. Are there any other questions from the audience? Someone has a curiosity or want to ask something on these two topics? So, if not, thanks again, Tommaso, for your very interesting and clear presentation.
Thanks to you.
Next event that will be next seminar that will be about Matteo Capone and Chiara Biagini, teaching communication or popularization. It's a different topic, but it will be. I'm sure that it will be interesting also. So thank again, Tommaso, and thank you all for attending this seminar.